Hello and welcome back. Today we are talking about section 7.5, constrained optimization, the method of Lagrange multipliers. We are going to try to tackle, again, like our previous video, the method of Lagrange multipliers in the context of applied problems, in this case one problem, but there was a previous example with another application. We're also going to briefly try to talk about this application of the Lagrange multiplier as a rate, which is a neat little tidbit. Let's see if we can get to our slide. Okay, so here's our admittedly slightly contrived setup, but we've got a salesman whose area is a 6-mile radius that surrounds the center of a city. So pictorially, what we're looking at is basically, if we picture the XY plane, I guess it's kind of our choice at the moment what to call these letters, but I think this will be consistent. And so we're looking at X miles east and Y miles north. So this is kind of exactly the orientation that we'd be looking for. And this salesperson is supposed to have a path that follows that circle, essentially. We're also told that his competition, in other words, the number of competing businesses, is given by some model of this form, and our task is to describe the location at which competition is minimized. That is, where is the competition smallest? Maybe gives them the best chance at getting new customers. Who knows? So our task is to figure out when this minimum level of competition is and exactly how many competitors there would be expected to. He'd be expected to run into. So our strategy here, again, we want to think, if we're trying to access this broadly and figure out what about this setup would imply to me that Lagrange multipliers were the strategy of the day, we would see that there is something about minimization. So minimum something, maximum something, that kind of feels like a 7-3 kind of question. But we also have to consider the fact that there's some restriction on this. Here is a combination of X and Y values that restrict what can happen with these inputs. So that right there sort of implies there's some kind of restriction on these numbers, and thus maybe 7.5 is actually the more reasonable strategy, because this is all about constrained optimization. So let's take a look. So the constraint function is a circle of radius 6. You may or may not remember from a college algebra or even a high school math class that the equation of a circle looks like, in the xy plane, looks like x squared plus y squared equals r squared, where r is the radius of it. So we're here looking at radius 6, so that would be r equals 6. We're going to look at our standard option, now becoming a little more familiar if you've watched all these videos, that we're going to take these first partials, set them equal to lambda times the partials of the constraint equation. So c sub x, we're going to go back to the competition function from the previous slide. It looked like 10 minus 0.1 x squared times y, just to remind ourselves where this came from. Derivative of 10 on its own, clearly going to get cut off by this derivative. And then with respect to x, the 2 is going to come down. We'll have negative 0.2 x times y. The y survives because it's a constant multiple to this, just like the 0.1. It's just getting multiplied here, so it's going to make it through our derivative. With respect to y, again, the 10 is out of there. Derivative is going to be 0. And then our only variable factor here is the y piece. All the rest of this 0.1 x squared is constant, so derivative of y is going to be 1, and it kind of just falls out of this equation. So our method is set all these things equal to one another. We've got our c sub x that we just tackled. We've got our c sub y. Those are the left sides here. And then inside of our parentheses here, we've got ourselves the constraint g sub x. So remember, our constraint equation was supposed to be, here's our circle. I guess I could take the moment to square 6 and make that a little tidier. And then the derivative of this, though, with respect to the variable stuff, is just 2x, with x as our variable, and then g sub y looks very similar with a 2y there. And then the last is literally just our constraint equation again. So there he is. Okay, these three equations together are what we're supposed to be able to use to come up with an x and a y that is a satisfactory combination to, in this case, minimize competition. So our strategy is often to solve for lambda. I thought in this one I would take a slightly different tact just to illustrate that there are other strategies here. So I'm suggesting that we solve for y. Now, this is one instance where we have to be pretty careful, and sometimes your instructor might give you homework problems where this subtlety is really important. If we want to take this expression and solve for y, it would make sense to take all of this stuff on the left side that is being multiplied to y and divide it out. This is always something that I want to be cautious of, because whenever we divide by variables, we run the risk of losing solutions. Now this deserves some red. So this right here is kind of a scary proposition. This is only okay if the thing we're dividing by, this variable we're dividing by, isn't 0. Because this cancellation on either side wouldn't occur if x were 0. We'd be dividing by 0, and that's a big no-no in math. So we can proceed with this as long as we're a little bit cautious. We've got our eyes wide open, as it were. And we notice that if we divide out this x, we have to include this extra little addendum here that reminds ourselves that x equals 0 wouldn't have made that a feasible option. So we divide out our x, we finish dividing out our 0.02, and we can get our y all by itself. Now, interestingly, there's no x's in this. It's y in terms of lambda, which is also a slightly different scenario that warrants our attention. But we're going to proceed like we have done in the past. We're going to take the results of this first equation, we're going to dump it into the second equation, and sort of see how this plays out. This gives us a result in terms of x's and lambdas. So here's our negative 10 lambda. There's where y used to be in that second equation. And we're going to get ourselves x in terms of lambda. So again, this is different from our previous examples in that we haven't gotten an actual value for lambda. We haven't solved for x in terms of y. We solved for one of the variables in terms of this Lagrange multiplier. So there are many possible, totally valid routes to this solution. But I'll just reiterate that I picked a slightly different one for this particular problem just to illustrate that there is this variation. So we've got the first two equations need to get combined so we can figure this out. Now we've got x in terms of lambda. We can take both of these results, both y in terms of lambda, which we already got, y was negative 10 lambda, this new thing that x is plus or minus lambda times the square root of 200, some weird number. There's our constraint equation, dump both of these exciting values in there, and actually solve for lambda, which is a slightly, again, different approach, but it's an interesting one. In particular, I'm being sneaky about this because I have an ulterior objective to finding lambda now. It's going to serve a purpose in our next example. So with all this exciting combination, the plus or minus kind of disappears, because if we take plus or minus and square, that's going to clearly leave us with something positive. We're going to have a lambda squared here. We're going to have a lambda squared here. And they're going to be like terms as a result. Square root of 200. Here's getting squared. Square root of 200 squared is going to be just 200. So we're going to have 200 lambda squared from this guy. We're going to have 100 lambda squared from this second one. So put those two together, and we're going to end up with 300 lambda squared. Finish solving, and we'll get ourselves a concrete value for lambda. We don't always need this, but it's certainly going to allow us to figure out x's and y's. One reminder of that is still on this slide. If you know what lambda is, x is just a short little jaunt away. Same thing for y. Okay, so now we know the value of lambda. We're going to figure out the values of x and y by going back to those equations we had in the beginning. We had x in terms of lambda, so once we dump in this 0.346 business, and multiply that by square root of 200, we're going to get a couple of options. I'm holding on to the plus or minus because, remember, x represents a horizontal distance, an east or west distance from the center of the city. I shouldn't be totally convinced that x has to be a positive or has to be a negative number, so I'm going to hold on to both of these possibilities. If x were like a price of some item or a quantity sold or something, then I should be convinced that negative is not a super useful contribution to this problem. But in this case, negatives make sense. Y works similarly. Again, we're taking that same lambda value at which this maximum is supposed to occur, multiply it by -10, take a number, we're going to get plus or minus anyway. So this gives us 4 combinations of values, and yet one more piece of excitement. Remember all the way back a couple of slides ago when we said, oh yes, we can do this math, but only if x were non-zero. Well, okay, well what if x were 0? There's no particular reason to believe that not going east or west at all from the center, just going north or south to the top or bottom of his little, the salesman's little circle of restricted path. There's no particular reason that to believe that those couldn't be locations where competition could get minimized either. So we've got to consider that as well. So once we know that x equals 0, we can get constraint values of plus or minus 6. So now you might notice these 4 numbers get combined. Then we have another 2 pairs of numbers where x is 0 and y could be positive or negative 6. So I decided, hey, let's just, since we have to test and see which of these things actually gives us a minimum, why don't we just put them into a little table and see what all this plays out. So these first 2 options are the 2 from x equals 0, and then the other 4 are the different combinations of values where either x or y is positive or negative. So here's the both negative option, here's the x negative, y positive, other way around, and both positive. So you notice there's some repetition here. For instance, if the y value flips from positive to negative, that doesn't appear to change the output. Spoiler alert, that's because our competition function had a y squared in it. So if you square a number and it's negative, you're going to get the same result. So all these ones, this negative 3.46 and positive, and this 3.46 with the exact same x values. So here's negative 0.49, and we've got a repetition between these 2 guys. So in any event, we're looking at all of these outputs and saying which one of these would be the smallest. Well, we've kind of got a tie for location. These both give the same output. And so when we plug those in there, this gives us the smallest value. If you look back at our original slide, the thing we were asked to find was the minimum competition. So we can say, okay, minimum competition is about 1.69, presumably an average of some sort, businesses. And that would be, here's our interpretation, 3.46 miles north. So if we're looking at our little circle again, I'll try and most likely fail to draw a convincing circle freehand. But here is some semblance of that. 3.46 miles north, and then 4.9 miles either east or west of the center of the city. So these 2 spots correspond to where competition would be smallest. So this would be good neighborhoods for this business person to go hawk his wares. Last topic for the section is a notation, the notion of this Lagrange multiplier, this lambda thing, as basically being its own rate of change, which is kind of an interesting way to think about this. There's a neat little mathematical construct for this, but essentially the claim is that if we have some function we're trying to optimize, find the max or min, it's got the constraint, same notation as our original definition, this k thing being the constant that all the variable stuff in our constraint would be set equal to. It turns out that if you made some small change in that constant, then lambda is exactly what we would expect the change in the magnitude of that maximum or minimum to be. In particular, the way we can express this would be something like the change in this max is approximately the same thing as lambda times the change in that k value. So as a quick example, you remember I said I had chosen in that competitor's word problem there, I had chosen to solve for lambda semi-intentionally. And the reason is that if we try to go back and use some of these numbers that we had from before, we can say the minimum value we found was 1.69. The k, here was our constraint formula. So k was this constant on a side by itself. Well, okay, so if k increased by 1 unit, in other words, if this constant on the right side went up to 37, essentially. Well, we could go back and recompute this whole minimum value thing, although that was slightly arduous. It turns out that this Lagrange multipliers thing gives us an approximate rate of change. So it says, okay, if we want to know how much would this minimum value change? Right now it's 1.69. If we increase the radius, so the salesperson's path around the center of the city gets slightly larger. Remember that we actually computed lambda before? So what we're basically saying is that this change in m was approximately lambda times the change in k. Well, k went up by 1. Lambda was negative 0.436, whatever. So we're estimating that the change in competition would be negative 0.346, the exact same value as lambda. Or interpreting that in some context, we're saying the minimum number of competing businesses would drop by about 0.346. So just as an example, if our constraint had gone to, it had dropped, let's say, to 34 instead, in other words, our change in k was negative 2, then we would see instead that the change in m would be something like, well, our lambda, so can't get away from that, negative 0.346. And since we're dropping by 2, we would say, okay, our circle is getting slightly tighter. The radius isn't quite as big because it's the r squared is only 34 now. And so our competition level would go up. We're imagining the closer to the city, the more center of the city, the more competition. So 2 times 0.346, approximately 0.7 more businesses he would run into on even at the minimum competition location. Okay, that's 7.5. We'll be back for 7.6 in another video.